So if the iPad doesn't work, then I have this board behind me, and
Okay.
I can directly write on that one. Okay.
Yeah, that works. That works. Okay, so very good morning to one and all. So welcome to the final day of the STEMS 2021 qualifier camp. So we hope you have been enjoying the string of talks we've had over the last 2 days. So kicking off day 3, I'm deeply honored to introduce Professor Jaikumar Radhakrishnan from the prestigious Tata Institute of Fundamental Research, Mumbai. He obtained his BTech in Computer Science and Engineering from IIT Kharagpur and his PhD from Rutgers University. His research interests include combinatorics and communication complexity. In his illustrious career spanning decades, Professor Radhakrishnan has held various positions in various universities across the world, including Chicago, Hebrew University, Jerusalem, and Japan Advanced Institute of Science and Technology, and many more. He has published numerous research papers and has given at least as many conferences. He was bestowed with India's highest honor for sciences, the Shanti Swarup Bhatnagar Prize in 2008, and he was also elected the Fellow of the Indian Academy of Sciences in 2007. So today, Professor Radhakrishnan will take us through an exciting road into the world of entropy and information. So without any further ado, Professor Jaikumar Radhakrishnan.
Yeah. Thank you for the invitation, and thanks to everybody for coming on a Sunday morning. So yeah, the topic of our discussion today is entropy and information. And so the way it's going to work is I'm going to show you some slides, and we will start things off on the slides, and then I will start writing something using a tablet. Okay. So if I'm able to manage the technology, that's how we want to do this. Okay. All right. Good. So let me start with a question which is called, so the Loomis-Whitney inequality. So I understand that there are people in the audience at various levels. So I will come to entropy and information just in a little bit. I want to motivate it using this little example, which seems to have nothing to do with entropy and information. And later on, we will see how ideas of entropy and information will help us find a simple answer to this question. So what is the problem? So you have n points in three-dimensional space. Okay. So some of these points might be aligned one above the other or one besides the other, and so on. So you project all the points to the xy plane. Okay. And you get n1 distinct points. The number of distinct points you get is n1. I hope everybody can see my pointer. Yeah. And then everybody can see my pointer, right? Yeah.
Yes, sir, we can see your pointer.
Yeah, it's visible. Okay. Then if you project on the xz plane, you get n2 points. And then you project on the yz plane, you get n3 points. So you project downwards this way, and you get n1, n2, and n3 points. And the inequality of Loomis and Whitney says that n1 times n2 times n3 is always n squared. Yeah. It's always at least n squared. And suppose you wanted to prove this. Yeah. And I'm going to now give some sort of an approximate answer to this question. And then we will see how to formalize that answer using entropy, okay, and information. Okay. So just to make sure what I was trying to say. So here are, you see 27 points. If you project them downwards, you get only 9 different points on the xy. And similarly, you will get only 9 points on the yz and xz. And their product, yeah, 9 times 9 times 9 is exactly 27 squared in this case. And I'll invite you to think about other configuration of points and see that always the product of these 3 numbers is at least n squared, yeah, n being the number of points. Now, why should this be true? Yeah? And let us give some sort of proof here. I don't know why this. So this is something, this is some way maybe a computer scientist might think that, to describe n points, I need log n bits. Yeah. Now, what log n here to me means log to the base 2. Yeah. So if you want to say, describe 1 in 8, so there are 8 possibilities and you want to describe one possibility, you will need 3 bits of information. 16, you need 4 bits of information. So the number of bits of information needed to describe a point is log n. Okay. And now, on the other hand, if somebody tells me the projection on the xy plane, they give me log n1 bits of information. Okay. And suppose they tell me the projection on the yz plane, they give me log n2 bits of information, and similarly log n3 bits of information. So together, by knowing the 3 projections, I get log n1 plus log n2 plus log n3 bits of information. So I'm still being a little vague. What is information? What is all this? But just play along. Yeah. So log n1 plus log n2 plus log n3 bits of information. And once you tell me the 3 projections, yeah, if you tell me where the point fell on the xy plane, where it fell on the yz plane, where it fell on the xz plane, I'll be able to uniquely reconstruct the point. So instead of telling me the log n bits, you might as well tell me these 3 bits and I get all the information I need. So however, I don't know where this is. Yeah. I get each coordinate of the point twice. If you give me where the point fell on the xy plane and where the point fell on the xz plane, I get the x coordinate from both of them. Similarly, I got the y coordinate from 2 sources and the z coordinate from 2 sources. So strictly speaking, if we believe all this, then log n1 plus log n2 plus log n3 should actually contain twice the amount of information as n. Okay, so there are many things I'm asking you to believe. So first of all, that there is something called information, and information can be measured in bits, and logarithm of the number of possibilities corresponds somehow to information. And when you have information arriving from different sources, we can just say that we have got twice the amount of information. And we should be able to write this inequality. So 2 log n is the amount of information in the point. The amount of information on knowing its projections is log n1 plus log n2 plus log n3. So these 3 numbers together must give me twice log n. Okay. And now you just take anti-log. Every log is to the base 2 here. So you get that n squared is less than n1 plus n2 plus n3. Okay. End of proof. Yeah. And the question is, does this even make sense? Okay. Yeah. And the rest of the talk will be somehow to, so you see how little we had to manipulate in this. No complicated calculations, no thinking how many points are in the first plane, second plane, third plane. Everything has just come out very easily. But if you believe such things, you can prove many things. We'll have to now make sure that all this can be formalized. So at this point, if there are any questions, I can, yeah. So yeah, I'll just pause for a minute.
Sir, there is one question in the chat that like which base currently you are using? Is it base 2 which you're using?
So in the rest of the talk, mostly my logarithms will be to base 2. And when I say exponentiate, I mean take 2 to the power. Okay. But there might be a situation where I need usual logs to the base e and exponentiation to the e to the power something. Then I'll tell you. Okay. Yeah, so okay. Now, yeah. So I want to just put down a quote from Christos Papadimitriou, who's a very famous computer scientist. And he said this in the context of the P versus NP problem. So successful ideas in science are those that are pervasive and invasive. Okay, they appear everywhere and they sneak in to situations where they are not expected to appear. Okay, they are elegant and methodical. Okay, and are open to extensions and variants, and answer an objective necessity and capture a widespread but diffuse sense of dissatisfaction in a scientific community. Okay. Now, I would like to convince you that entropy also fits this definition of an important idea. Okay. Yeah. So I'd just like you to keep this in mind as we now discuss information. Yeah, we will do some mathematics on the tablet. Okay. So now this is my first challenge. I'm going to unshare the screen and then move to my tablet. I hope that is still on. Okay. Otherwise, I might fiddle for some time. Please don't go away. I should be able to recover from any disaster. Okay. So I'm stopping sharing here. Good. And okay. And now I'm in Zoom, and I say stop broadcast. Are you able to see something?
Yes, we can see it.
Yeah. All right. So I hope everybody can see everything. Yeah.
Yes, that's perfect.
Yeah. Good. Okay. So what is the plan for today? So the first thing I'm going to do is I'm going to show you some situations. Okay. We will try to set things up so that we can talk about information properly. And then the second thing is we will at this point still not know a proper definition of information. So I will I'll try and motivate a pragmatic approach to information. And this will involve measuring information in terms of cost of transmitting it. And this will lead us to what is called Shannon's entropy. Then, so this is one way of approaching entropy. There is another aspect of entropy, and I believe I will have time for that. So I wanted to give you the other way of thinking about entropy, which is what is used in information theory, and that is and then we will go back. Is this, yeah, so that's the plan. Okay, let's see. Yeah. So when somebody tells us something, we believe that we've received information. Okay. Now, what we will do is we'll try to understand why do we say that we received information. So the way it is going to be modeled in our discussion today is that before somebody tells us something, there is some uncertainty. Okay, so information, when you receive information, some uncertainty is removed. Okay, so that is the fundamental philosophical principle we are going to adopt. So uncertainty about what? Okay, so it can be a coin toss. I'm sorry. So when you toss a coin, you have two possibilities. Maybe one of them is called head and the other is called tail. And you have associated probabilities with the two possibilities. Maybe it is 0.5 and 0.5. Or you might just pick a random letter from a book. Yeah, you just opened the book at a random page and picked out one letter. Okay. So in that case, yeah, so I'm sorry, I keep doing this. I don't know how to avoid this. So in this case, you have maybe, yeah, you have 26 possibilities, and you have corresponding probabilities. Yeah, so we don't know, different letters have different probabilities. Apparently, yeah, E has the highest probability, about 0.11, and Z has probability 0.0044. This is something that people have measured empirically, and you can find it on Wikipedia, etc. Okay. So now there are experiments like this where you either toss a coin, pick a letter at random, or some other probabilistic event that you have modeled in advance. You know the probabilities, and you want to observe that the outcome of that experiment and then transmit the outcome to somebody. So now our two characters enter the game. So there is, what did I do? Is there some way to, I keep messing this up, but anyway. Yeah. Okay, so there are these two people, Alice and Bob. Alice observes the event, the X. So what is X? X can be head or tail, or it can be an element in this set. So depending on the situation, one of these experiments is performed, a coin is tossed, and then Alice has to send a message to Bob, some sequence of bits. Just 1 second, let me figure this out. And Alice sends Bob some sequence of bits. And from this, Alice decodes and recovers X. So now we have many situations. So you have this coin toss. Where you have head and tail, and the probabilities are 0.5, 0.5. And there is this other situation where you have head and tail, but this had probability 0, this had probability 1. Or you had head and tail, and you had probability 0.75 and 0.25. Yeah, okay. So when Bob gets to know the outcome of this experiment, I would like to think that in this case, Bob did not get much information. Why? because Bob already knew that it was going to be tail. Okay. In this case, Bob had no idea it's going to be head or tail with equal chance. And when Alice conveys to him that it was head, okay, he got information. He managed to rule out 50% of the possibilities. Okay. In the third case, we at the moment don't know where to place this. Okay. It looks like it is slightly balanced. Most probably it is going to be head. And when Bob gets to know the outcome, most of the time he would say that, yeah, that's what I had guessed anyway. So you're not giving me too much information. Okay. So we would try to formalize all these notions of information. So let me move from this to a bigger alphabet. Okay. So right now I'm just talking about coin tosses where you have head and tail, and that means you have only two possibilities. But I want to now do some examples with slightly bigger number of possibilities. So let us say that, yeah. So this is how we will be modeling our uncertainty. Now I want to tell you about transmitting information. Okay. So let us say that you have these 5 letters, A, B, C, D, and E, and they have their probabilities. Yeah. And let us say this is 0.1, 0.15, 0.17, 0.18. I don't know. I also have an F apparently. Yeah. And yeah, so unfortunately, is this? Yeah. I hope it's adding up to 1. Yeah. Okay. Yeah. All right. So suppose there is some experiment, and let's call this experiment X. Yeah. This is our experiment. And this experiment has these 6 outcomes, and they have their corresponding probabilities. Okay. And Alice and Bob know this. They know that Alice is going to perform this experiment, and she's going to get these outcomes. And she wants to transmit this information to Bob. So when they are discussing, they are in the same room. Then Bob has to go away, far away, and then he's quarantined there. Okay. And Alice performs the experiment in her lab, and she now needs to transmit this. Okay. So what do? They decide to use an encoding. So they say that to each of these 6 letters, let us assign a code word. Okay. So you have A, B, C, D, E, and F. And to each of them, I want to assign some code word. Maybe I say 0, 0 for Alice. For Bob, I say 0. Yeah. So if Alice performs the experiment and sees the outcome A, she's going to say 0, 0. Yeah. And okay, maybe I should make this. Okay. And if she sees B, she's going to say 0, 0, 1. Okay. So right in the beginning, they sit down and decide what should be the optimal coding. Now, optimal in what sense? Yeah. So let us say that they would like to minimize the number of bits transmitted. Okay. Now, the point is that number of bits transmitted depends on the outcome. If the outcome was D, then she actually transmits 4 bits. If the outcome was A, she transmits only 1 bit. Okay. So when we say minimize the number of bits transmitted, what we really mean is on average. So under this encoding, under this encoding, and with these probabilities on the top, so these probabilities, what is the cost, or what is the expected amount of number of bits that Alice will have to send? Well, with probability 0.1, she will be sending 3 bits. With probability 0.15, she'll be sending 3 bits. And with probability 0.25, she'll be sending 4 bits. So on an average, this is the amount of transmission. And this quantity I'm going to call T of X. Okay. So so are there any questions at this stage?
I think there are no questions. If people have, they will unmute.
Sorry, people?
If people will have, they will unmute themselves.
Okay, yeah, please feel free to unmute and ask too. Yeah. So we have this scheme. This is the experiment Alice is going to perform. And they have decided on this encoding. And the cost of this encoding is this quantity that I write here, right? Yeah, this quantity. And I'm going to give this a name, and that name is T of X. So if your X was this coin toss, then there might be the optimum encoding, and the cost of transmission in that will be T of X. Yeah, so there's somebody has a question. Can you please read it out for me?
Yes, sir. So the question is, can this be thought of making the expected value of number of bits used minimal?
That is correct. Yeah. So the formal thing is design an encoding so that the expected number of bits transmitted is as small as possible. Okay. Now, this problem, I'm sorry. This problem has been solved. Yeah. So, I mean, many of you who have done some basic algorithms might have been taught how to optimize this encoding. Okay. And one way to think about it is using a tree. Yeah. So let me. So So suppose, for example, we gave Alice the code 000. Yeah. So, sorry, the letter A, the code word 0. Yeah, unfortunately, my. 0, 1, 0, 1, 0, 1. Yeah. Okay. So the left branches are labeled 0, the right branches are labeled 1, and any sequence of zeros and ones will correspond to a node in this tree, because 0, 0, 0 means this one. 1, 1 means 0, 1 is this one. Yeah. Yeah. So there's a question. Yeah.
So the question is, why are we using bits specifically in this case?
So right, we could use anything. You could use other alphabet. usually so this whole theory was invented in the context of information transmission. And at that point, we were modeling information using bits, and that is how things are stored in the computer using two levels of logic. And but information theory to other bases can also be discussed. There is no problem in the theory. I will be doing this in the language of bits. When you do other alphabet, then my trees will have more branches. Yeah, there won't be just 0 and 1. There'll be more branches. Okay. Now,
and sir, there's another question. Can you please explain how you define the nodes of the binary tree once again?
Sorry. How do I do what?
Define the nodes of the binary tree.
How I define the nodes of a binary tree?
Yeah. Can you just?
So I don't know what the question means. So I just draw a tree where every node has two branches, one called left, one called right. And in the left branch, I write 0, and in the right branch, I write 1. That's all. Okay. Sorry. Now, maybe the question was, how did I put a box here? Yeah. So how did I manage to why did I put a box here? I'm just trying to say that when I think of the string 0, 0, 0, this one, yeah, then in the tree, I think of it as this path, 0, 0, 0. If the string was 0, 1, then I would have thought of it as this path. Okay. So it's nothing very deep going on here. Every string can be thought of as a node on the binary tree. All right. Okay. So what are we trying to do? We are trying to place these 6 letters A, B, C, D, E, F on this binary tree at various places. Okay. 2 of them should not occupy the same place, because if the corresponding code word is transmitted, Bob will not know which of the 2 was intended. So we should assign different nodes to different symbols or different outcomes of our experiment. And we should minimize that those nodes are as high as possible in the tree, because the cost of transmission is how far you are from the root of the tree. Okay. Now, so the question is just this simple thing. That is, you have been given these letters of the alphabet, and you have been asked to place them on this tree so that there is no ambiguity and the cost of transmission is as small as possible. Okay. And there is a way to do this called Huffman coding.
Sir, I have a question.
Yeah, please.
Sir, does the cost of transmission mean the number of bits that are being used?
That is my definition. The cost of transmission is the number of bits that are being sent.
Okay, sir.
Okay, yeah. So that is why the average cost is this. Because if A was transmitted, three bits will be sent. If B was transmitted, B had probability 0.15, and again 3 bits will be sent. But F had probability 0.25, and in that case, 4 bits are going to be sent. Okay, yeah. So there is this method called Huffman coding, and what Huffman coding does is it gives you an algorithm for building this tree optimally. The best way of assigning these, putting these square boxes on this tree so that the total distance from the root, the average distance from the root, is as small as possible. And how do you compute the average? You take the distance, multiply it by its probability, and add them up. Okay, yeah. Now, yeah, so I'll come to this question later. Yeah, so let me just say one more thing. There is a certain thing we need to take care of while placing these square boxes on the tree. If we have a tree like this, and we place one box here, sorry, and another box here, this is not allowed. Why is this not allowed? Because when 0 and 1 is transmitted, suppose this corresponded to the letter A and this corresponded to the letter C. When 0 and 1 is transmitted, the Bob, on seeing 0 and 1, doesn't know whether he should wait further for another 0 and 1, or he should already stop and assume that it is A. Okay. So we will assume that our encoding is prefix free. So no code word should be a prefix of another code word. Okay. So the problem of minimizing that we are talking about now is try and find the smallest code word, try and find an assignment of prefix free code words. Yeah, no square box should sit under another. Okay, so that the total cost, the average cost, I keep saying total cost, what I mean is you multiply the distance of the node with its probability and you add them up, and this should be as small as possible. Okay. Yeah. All right, so if there are any questions, I will answer them now, and otherwise I'll move on.
Sir, there's a one question, but it's more of a philosophical. We can take it in the end. I guess you can continue now.
All right. Okay. Yeah. So now let us consider the simple case where the probability of A was, let's say, half. The probability of B was 1/4, and the probability of C was 1/4. So there are only 3 outcomes. So what would you do? And I think if you just think about it for a minute, you will realize that maybe we should put A here, and yeah. So we should try and keep A closer to the root and move B and C down. And what is the cost here? Well, the cost is, with probability half, it is 1, and with probability another half, it is 2. So the cost here is about, I don't know, what did I say, 1.5? Yeah. And if you ask, what was the length of the code word assigned to A? A was assigned a code word of length 1, that is 0. B was assigned a code word of length 2, which was 1, 0. And C was assigned a code word 1, 1, which was length 2. And what do these numbers, yeah, length of the code word and the probability, have in common in this example at least? If you think about it, the length assigned to A was the log to the base 2 of the probability of A. What is the probability of A? Half. You take its reciprocal, you get 2. You take its log, you get 1. And in the case of B, the length of the code, which is 2, yeah, and that also turned out to be so. At this point, if you play around with some examples, you will see, or at least Shannon saw, that there is a certain quantity associated with the distribution X, which somehow seems to determine the cost of transmission. And so now let me just define entropy for you. Yeah, so the entropy of X. Yes, so X was an object like this, where you had characters on the symbols on the top and probabilities at the bottom. Yeah. So what is the entropy of X? Well, suppose there were K possibilities, 1, 2, 3 to K, and there were the corresponding probabilities P1, P2, P3, Pk. Then the entropy, they use the letter H for defining entropy is that is P1 log 1 over P1 plus P2 log 1 over P2, and all logs are to the base 2. Yeah. And this quantity is called the entropy. Okay. And Shannon's theorem was so that is the cost of transmission is very closely tied to this entropy. That is, no matter how you do the encoding, you will always need entropy amount of cost. First point. The second point is that if you give me the probability distribution, there is a way of encoding which will achieve at most h of x plus 1. Now, h of x will not be a rational number or something, because we are taking logs, we will get all kinds of crazy numbers. But somehow our idea is to associate with each random variable or such a random scheme a quantity, and that quantity is called entropy, and this is what Shannon asked us to use for entropy. Okay, so if there are any questions now?
Sir,
is the bit connected to the probability?
Sorry? Say
Is
that
the
again.
bit connected with the probability? Number of bit while computing the TX?
That's right. So, I mean, the number of bits that we assign to a particular symbol depends on its probability, because if somebody has very high probability, we should try and give it small code words. And if something has very low probability, then we should give it long code words. We should not assign long code words to things that appear very frequently, because then our cost of transmission will become very high. Okay. Yes.
Suppose we assign the bit for a probability pi greater than log 1 by pi, then tx greater than 1 by pi plus something, so that the tx exceeds x plus 1. We can't have such a bit. Can't we have such a bit?
Say that again. Yeah.
Suppose we assign some bit to pi with the event of less than log 1 by p1, so that the summation is lesser than equal to hx. So tx is less than equal to hx, it's coming. We can assign such bit to that probability.
Yeah. So you cannot assign a bit to any one symbol, forgetting about the other symbol. So right now, as you can see, there are k symbols here. You have to assign a bit string to each of them. Okay. So look at this thing here. Yeah. Now you have k possibilities. So to the outcome 2, you are going to assign what? So you said, let us assign a bit. Okay, so maybe to the outcome 2, we assign 0. Then we cannot use 0 for anybody else. Okay, so to each, yeah, maybe that was not the question. Yeah.
I am just asking that suppose for the 2, I am assigning a bit which is less than log 1 by p2. For each of this I am assigning the bit to be less than equal to log pi.
Log 1 over pi.
1 over pi, log of 1 over pi.
When you say bit, do you mean a bit string? Because log 1 over pi might be a number like 7. Okay, so then
I am assigning 6 to that pi, and after that for the next other, in such a way we are assigning, then the summation will be less than hx. The tx will be less than equal to hx.
Yeah, so if you do that, yeah, so your question, okay, so now I think I understand. So if you assign bit strings whose length is less than log 1 over pi, it will turn out that one of them will be a prefix of the other, and such an assignment will not be valid. So Shannon's theorem says that if you assign prefix-free words to this alphabet, then you will incur a cost of at least h of x. Okay. So your proposal to assign less than log 1 over p of x is not invalid, except that if you try and do that, either your two different symbols will get the same string, or some string will be below the other.
Okay, sir. Got
This
it.
is
Thank
something
you.
you have to check. Yeah. Okay. And all right. So this is one pragmatic approach to entropy, and both. So let me just. So I was actually planning to tell you the proof of this, but somehow the speed at which I'm going, I will not be able to give you the proof.
I have a question.
Question.
Yes. Sir, in general, is LA equal to log of 1 by PA? You have written above that L subscript A equal to log of 1 by PA, log 1 by PA. So does it hold in general?
No. So in these examples,
All right.
we used, it turned out that it was log 1 over PA. So we might guess that maybe log 1 over PA is the correct answer. But Bigyan suggested that maybe we can use something less than log 1 over pi. So the actual answer is that you assign, so to get this result, to be able to prove this, yeah, what you do is you assign LA. I don't know why my pen is not working. I don't know what I did. 1 second. Let me sort this.
Select the pencil option. Yeah.
LA, you assign it So I think Bigyan was just too greedy. When I said log of some number is 7, you assign 7, don't go for 6. But if the log is something like 6.5, then you assign it a code word of length 7. Don't round down, round up. Okay, this symbol means round up. And if you use these numbers, then it turns out that there is always a way of assigning code words of that length. In general, if you have a prefix-free code where the ith symbol has been assigned a code word of length li, and then this inequality always holds. Okay, I will let you check this. So this is called Kraft's inequality. On the other hand, and this is what many of you are thinking about, if this inequality holds, yes, somebody gave us some numbers L1, L2, L3, and so on, and somehow it turned out that this inequality holds. Then it is possible to find boxes, place boxes on the binary tree so that the ith box is at a distance Li from the root, and no box is on the path to any other path. That is, the corresponding code words are prefix-free. Okay, and since you are rounding up, you would have incurred 1 extra over what the entropy calculation was using. That is why there is a gap of 1 between the entropy and what you are able to achieve. Okay, but in general, if you use Huffman coding, you might get something which is better than this naive way of rounding up. Okay, so let me just stop with this. Now, can somebody tell me why my screen is not moving up?
I think you should set it to smooth scroll and not page by page, I think.
Okay, and if I do page by page, how do I go to the next?
Not to page by page. I think if you should smooth scroll, I think it will also, I think, show the whole sort of, you'll only see part of the page where you write. You are using Notability, right? What are you using?
Something called Note or something. So yeah, so I don't know.
No, then I'm sorry. I'm talking about something else.
Yeah, so
no, I should retract my suggestion.
Okay. So yeah, I don't know what I just did, which messed this up. Okay, so let me do this. Let me just close and come back, and hopefully it doesn't remember what I did. No.
So Jaikumar, maybe one way is like if you try using 2 fingers to pan, does that work?
I'm trying to. I'm trying. I don't know why it got stuck like this. Okay, so let me do this. Let me just start a new document.
Maybe you can choose a new page or page insert option, if there is such.
Yes, does anybody have an idea?
Maybe if you choose a new page or say page insert, maybe it will give you
The
a
other
new
thing
page.
is, Jaikumar,
There
on
is
the
such
top,
an
there is a done or something. Can you just click that? That also doesn't work? Okay.
So, now I don't know what I did, but
You just close the Notes app and or reopen it back maybe.
sorry.
Just close the Notes app and reopen it back maybe.
Okay, okay. So this was what I was doing, and now it is scrolling. So I just, yeah, it just got jealous that I was going to use another document, and now it's working. Yeah. Okay. All right. Sorry. So, all right. I'm going to now.
Sir, another doubt.
Yeah, please go ahead.
Is the Shannon theorem valid only when we are coding with Huffman coding?
Which analysis? No. Okay, so let's, thank you for the question. No matter how you try to encode, yeah, the amount of the cost that you will need for transmission will always be at least h of x, provided you use prefix free codes.
Okay, sir.
Okay.
Thank you.
And there is always a way of encoding so that you will not need more than h of x plus. Okay. So entropy seems to capture the amount of information, at least from this pragmatic way point of view, that we want to transmit some information, and the cost of transmission should be considered the entropy in the random variable x. Okay. Okay.
So basically, for the first inequality, we are having that for all coding, and the second inequality we are having there exists a certain coding.
Yes. So actually, t of x is defined as the minimum over all coding. Okay, then there is no, I don't have to use different quantifiers. Let t of x be the minimum transmission which the cleverest person can invent for this random variable. Then t of x will be at least the entropy and at most entropy plus 1.
So Jaikumar, this is even if it is a non-prefix code or?
No, this is only for prefix free codes. Okay. So this is, yeah, it is true for something called uniquely decodable codes, but I'm right now, let us just say that it is true for prefix codes. All right. Okay. So given that I'm slightly running out of time, let me move on to a slightly different view of entropy, and just so let us recall, we had this example of, and where you had 0.5, 0.5. And then there was this example where you had 0.75 and 0.2. And somehow intuitively, at least, we would like to think that, I don't know about information, but uncertainty in the first example, yeah, uncertainty in this example is more than in the other example. And how do we, if we use our pragmatic consideration, whether it is the first experiment or the second experiment, the best encoding is give 0 to one of the outcomes, 1 to the other outcome, and your cost will always be 1. So the cost of transmission somehow is not able to differentiate between these two possibilities. In general, there may be some situations where things are incomparable and we will not be able to tell which one is more uncertain than the other. So now I want to give you a slightly different way of thinking about the situation of information, so that some sort of a natural difference arises between these two settings. Okay. And let me start with the following. Suppose you have a set A, and it has some symbols, x1, x2, etc. Now, I should use x, k maybe, yeah. And suppose so there is an experiment which has these k possibilities. And now I perform this experiment again and again, n times. And I record the outcomes. So the outcomes will be now strings, which will look like x1, x2, x1, x1, x3, and so on. Or x1, 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 x5, x7. Yeah. So here n was 5. So you have all these outcomes. And each of these outcomes so I'm performing this experiment independently. Yeah. Each trial, I again get the next outcome independent of what happened in the past. So each of these symbols, each of these sequence of symbols has its own probability. Yeah. And I don't know what this is. Again, I'm sorry. Okay. So each of these sequences has its own probability, and I could write down all possible, so k to the power 5 sequences here, and write down their probabilities. Yeah. So if you just had a set, and if you take its Cartesian product with itself, if you take the n-fold Cartesian product, the number of symbols, number of sequences you get is k to the power n. So let me just draw this. So initially you had, if there was no possibilities, it was 1. If you did a to the power 1, then you got k. Let me draw k here, k squared. So as you take Cartesian products, the number of possibilities grows exponentially, and the base of this exponential growth was k. All right. So I want you to focus on this base of this exponential growth. Yeah. And entropy has something to do with the base of the exponential growth. Base of the exponential growth of what? Just because I have put some probabilities on these sequences and these elements, and then as a result, I received some probabilities on these sequences, it doesn't mean that the number of possibilities goes down. The number of possibilities is still k to the power n. If I do n experiments, the number of possibilities is still k to the power n. But are all those possibilities equally likely? Are there some possibilities which are more important than the others? Okay, so these are the questions to ask. And when we ask this question, I will try and convince you that entropy arises immediately. So let me draw a picture. I don't know how to do this. Okay, so this is the set a to the power n. Yeah. So it has how many elements? K to the power n elements. And some of those elements have high probability. Some of them have maybe not so high probability. And I ask you, fix any epsilon between 0 and 1 and construct a set a epsilon n so that the total probability of a epsilon n is at least maybe. So all I'm saying is that there are many strings. I don't want you to pick all the strings. but pick enough strings that you have substantial probability. And ask, how big is this set? Okay. So in our coin toss example, I'm really sorry about this. In the coin toss example, when the probability was 0.5 and 0.5, yeah, then each such sequence of length n would have had probability 1 over 2 to the power n. Yeah. All these sequences would have had 1 over 2 to the power n. And even if you wanted to pick up, accumulate a total probability of half, you would roughly need 2 to the power n, maybe these many strings. Yeah. Whereas if it was the other experiment, where you get then the sequences that you have will typically have more heads than tails. A typical sequence will have 0.75 n heads and approximately 0.25 n tails. Okay. So most sequences are not balanced. And you ask how many such sequences are there which have about 0.25 n tails and 0.75 n heads? Well, it is our usual binomial coefficient n times 0.75. And this is a much smaller number than this. Okay. If you avoid balanced strings and if you go for strings which have a skew in their distribution, the number of strings you get becomes much smaller. Okay. And since most strings, all the probability is basically sitting on strings like this, you can. I don't know what happens. Really.
Maybe scroll down for a long distance and then come back here.
I should scroll down and then come back like, I see. Okay, maybe. Let me try. Okay, next time. Yeah. So I drew this picture for you. There was a box and then there were strings here with various probabilities. And I fixed an epsilon. You can fix any epsilon. Okay, so let's say epsilon is 0.1. So you're trying to get a set which captures 90% of the probability. If you try and go for 100% of the probability, then you have no choice, 2 to the power n, because you have to pick all the strings. But if you fix and say I'm satisfied with 90% of the probability, the number of strings you will pick will look like 2 to the power n times the entropy of x. In other words, if you take this set A epsilon, look at how many strings you need. So try to get the smallest set which will pick up 90% of the probability, and you take the log of this to the base 2 and divide by n. Okay, this number, as n tends to infinity, goes to the entropy of x. Okay. This is a general principle. Give me any distribution. So we had that possibility of letters. Don't focus on one letter at a time. Focus on n letters, as if you had performed that experiment again and again. And then you ask, essentially, how many outcomes exist? Yeah, if you just want, if you're willing to ignore a small probability, and then the answer turns out to be 2 to the power n times entropy, which means, no, anyway, that is, which means that it doesn't grow as k to the power n, it grows as some other base to the power n. And the base here is 2 to the power entropy of x. So the entropy of x is the essential property of a probability distribution, which tells you how much the content increases as you perform the experiment again and again. And of course, the content increases exponentially, but the base of the exponent, base of that exponential is 2 to the power entropy. Or if you were to take the log and divide by n, that number will start looking like the entropy. And that was another way of thinking about entropy. All right. So here is what I'm going to do. I'm going to go back to the Loomis-Whitney problem now and tell you how all this way of thinking about entropy somehow gives us that inequality. All right. So let me figure out how to unshare this. Stop broadcast, I suppose. Unshare. And now let me go here and share again. So, Amit, can you tell me if everybody is able to see what is there on my screen here?
Yes, sir. Currently, we can see, can we quantify information like this?
That's right. That is the heading. Yeah, good. Okay. So, yeah, so here is what we have done somehow messily on my tablet. That is, there was something called X, which was a model of a random experiment. And there were n outcomes, and they had their corresponding probabilities. And the entropy of such a scheme, we decided to define like this. The 1 over pi, I have called it pi, but I have put a minus sign here, so don't be alarmed. Okay, so everything's okay. Yeah, this is what we know. Now, what do we know about entropy so far? So the entropy, it measures the uncertainty in X. And we had two ways of thinking about it. Yeah, one was from the pragmatic consideration of transmitting X. The other was at what rate does the uncertainty grow? That is, how many different possibilities do I need to think about as I repeat the experiment? Okay, if I'm willing to do away with a small probability of error. Also, the entropy of a random variable, this is not too crucial. It just depends on the underlying probabilities. How you name your outcomes, whether you call it head or tail or 0 or 1 or, today or tomorrow. Yeah, it doesn't matter. The formula, of course, uses only the PIs. The first row of this scheme is irrelevant, as it should be. Yeah, and I have not been able to prove this, but if you look at this formula, and if you write this as pi log 1 over pi, and it looks like an average of some logs. Yeah, the average of some logs, average of logs is always at most the log of the averages. Okay, this you probably know this as the arithmetic mean geometric mean inequality. Yeah, or you can say that log is a concave function, whatever. Yeah, and as a result, when you take the log of the 1 over pi's with probability pi's themselves, you will get log n. Okay, so if you have n outcomes, your entropy will never be more than log n. Okay, this is a very important fact. No matter how you arrange the probabilities, or in other words, the best way to assign the probabilities so that the entropy is as high as possible is when you assign uniform distribution. And if all the pi's are 1 over n, you can check that the answer that you will get from this computation is log n. All right. So we have 3 facts with us. Entropy measures uncertainty. The entropy is just a function of the underlying distribution, numbers, and the entropy is never more than log n. I want to tell you one more thing. So if you perform the experiment twice, and first time you got the answer X, and the second time you got the answer Y, or you perform 2 different experiments and there was some correlation between the outcome of the first and the second, then instead of the table with 1 row, with 2 rows that I used to draw before, you will get this sort of a scheme. The random variable X has m possibilities, the random variable Y has n possibilities, and there are these corresponding probabilities. Okay, and this is again a scheme where you have m times n possibilities, and you can compute its entropy, and its entropy will be this. This is the same formula, just it so happens that our possibilities now have 2 labels instead of just a single label. They come in pairs. Okay, and there is something called conditional entropy. Okay, so let me just go back. Yeah. So h of xy, I'm going to think of as the amount of information I get when I'm told both x and y. Okay. H of x is the amount of information I get when I'm told only x. Okay. And the difference between h of xy and h of x is called the conditional entropy of y given x. So somebody has already told me x, and then on learning y, how much extra information I get. Okay, and this is the definition. This is the formula. Yeah, and it turns out, using similar considerations by the AFGM inequality or the fact that log is a concave function, you can check that h of y given x is at most h of y. You see, suppose somebody told, okay, so maybe I think I have a time to make a story. Yeah, so suppose you pick a person at random from the whole world, and then you ask them to say something. Now, they might say something in a language which they know, okay? So initially, if X is the, say, the nationality of the person, and Y is the language they are speaking, okay? So you pick a person at random and listen to them for some time. So you get two random variables, their nationality and the language, okay? And this has some joint distribution, yeah? If you pick somebody from India, there is a chance that they will be speaking Telugu or Kannada or Marathi or something. Okay, so what they speak, yeah, depends on the nationality. These are correlated random variables. If you pick somebody from India, they are unlikely to be speaking Swahili. Yeah, but initially, if you ask me what language is being spoken, I might have a certain amount of uncertainty. But if you tell me the nationality of the person, the amount of uncertainty in the language reduces, because now I'm able to guess better what the language is going to be. Okay, so if you condition on the random variable x, which in this case was nationality, the amount of entropy in y, the conditional entropy reduces. And this is a theorem. Yeah, we haven't proved this, but this is a theorem. And if you give me more information, then the amount of surprise I get, the amount of information I get from a new observation only reduces. That is, initially there was conditional information of z given x. If I know more, then I learn less. Okay, yeah. So these two facts are somehow true and can be proved using the arithmetic mean geometric mean inequality. Okay, good. So this is all we have right now, and I'm ready to go back to the Loomis-Whitney inequality. So I want you to remember three things. Entropy is at most log n if you have n possibilities, and these two inequalities. If you condition, the entropy only goes down. If you condition more, the entropy goes down even more. Yeah. And once you have comfort with these three inequalities, we are ready to state those rough nebulous ideas of information precisely. Okay, so remember you had n points in 3 dimensions. You projected them down, and suppose the 3 projections are P1, P2, and P3. So there was no randomness in the whole inequality. Okay, let me impose randomness. Let me imagine that I'm going to pick the point P out of these n points at random. So what does that mean? When I pick the point P, I get its x coordinate, y coordinate, and the z coordinate, and each of them is a random variable in its own right. And there may be correlations. When x is 5, the only possibility for y may be only 7 and 10. Yeah, and so on. So there is possibly correlation. These are not necessarily independent random variables. But let us just play along. P is x, y, z. And what is P1? The projection on the xy plane, just the pair xy. You understand? Yeah. To describe P2, you just have to tell me x and z. And to describe P3, you just have to tell me y and z. So what is the entropy or the information that I learn when I pick this point P? Well, it is h of x plus h of y given x, the amount of additional information I received on seeing y, and then the amount of additional information I received on seeing z given xy. Okay, everything is an equality here. P1, its entropy is h of x plus h of y given x. P2, h of x plus h of z given x. P3 is h of y given h of z given x, y. Okay. Yeah, so these are just somehow natural things that we would do from the point of view of information. Now notice that if you look at each column, yeah, h of x, if I add these three equations, I get h of x twice. H of y given x, I get here. And in this, I get h of y. But h of y is even more than h of y given x. And in the third column, here I had h of z given xy. And here I have h of z given x and h of z given y. Both these quantities are at least this quantity. So if I add these three numbers, h of p1, h of p2, h of p3, I will get at least 2 times this. This is what we were wondering. Yeah, are we entitled to say 2 times? And using the language of entropy, yeah, we are able to say that 2 times the amount of information in P is present in the sum here. And now, whatever we said vaguely in the beginning are completely justified. Okay, so there are many such combinatorial equations, inequalities, which you can derive just by imagining a probabilistic process and trying to ask how the information measures up. Okay, so I'll stop here. I'll just summarize. So there is this notion called entropy. I wish I was more systematic in describing it to you, but it is, you should look it up again, or yeah, do attend courses on information theory whenever you get a chance. So the entropy of a random variable or a random system X is defined by this formula. We gave some intuitive justification for this based on how much we should invest in transmitting this information. There was a notion called conditional information, which is very natural. How much extra information do you get when you already know part of the observation? And entropy is maximum in the most disorderly system, when every possibility is equally likely. Okay, and we justified the Loomis-Whitney inequality using these considerations. There is an article by David Galvin on the internet on entropy and counting. And if you like what you saw, please go and take a look at that. There are many, many examples of how entropy can be used in combinatorial studies. Entropy actually shows up in many other areas. Some even talked about physics in the chat and other areas. It comes up at very strange places, and here is yeah, and that's why I think entropy justifies, or at least fits, this requirement of a successful scientific idea. I myself found entropy in a very strange place. So I was trying to solve this puzzle on in Mumbai Mirror a few years ago, and this showed up. And I was probably not in the right frame of mind, and I noticed that poetry, the word poetry shows up, P-O-E-T-R-Y, and I did not count. And I thought, okay, I'm done. And I put the paper away. And then somewhere in the middle of the day, I realized that no, it doesn't involve all the 7 letters. Yeah, poetry doesn't have all the 7 letters. And I kept looking, and you won't believe it. It took me half an hour before I realized that it was actually entropy. Okay. So yeah, so then onwards, I have been saying I was satisfied with poetry until I found entropy. All right, so that's all I have to say. Thank you very much. I'll be happy to answer your questions. And yeah, please, yeah, if there are questions, I'd like one of the hosts to select them and show it to me. Or if you want me to read from the chat myself, I could do.
Firstly, thank you very much. I must admit this was an extremely lovely session. The way you derived the main formula of today, like in 2 different ways, like the first one being direct, and the second one being extremely built up intuition. So that I must admit was exceptionally beautiful. So like with the amount of passion with which you explained was also something which was really extremely lovely. So thank you very much for your and beautiful session today.
Thank you. Thank you.
There was one interesting question in the chat. So I'll just read it out. Entropy can be thought of as a disorder, although it's not the best way to describe it, according to a paper by Dr. Frank Lambert. Say, for example, during the Big Bang, everything looks to have come into order. Subatomic particles ordering themselves into well-defined quantum orbits, and atoms ordering themselves into molecules and so on. This seems to defy the prevailing definition of entropy using disorder. Does this happen because of the laws of physics were still emerging in the first few Planck seconds after Big Bang? And if not, how can this be better explained through the approach of linking it with information?
Yeah, so as you can probably imagine, I am not very competent to talk about these. I think there are situations even in the kind of information that I was modeling using probability theory as a base. There are connections, okay? So this particular notion of entropy was already anticipated in the physics literature even 100 years before in Boltzmann's ideas of disorder and things like that. But Big Bang is something I just don't know anything about. So I believe it is just that when you talk, the way we have set up entropy, we have decided a scheme, what our alphabet is going to be, and what the corresponding probabilities are going to be, and then we start studying things. Okay. I believe the correspondence there is not quite working out, because as we go along, perhaps the number of symbols itself expands, your alphabet is changing with time, your probabilities are themselves changing with time, and maybe the notion of entropy as we have formulated it is not applicable to that setting. Yeah, so unfortunately, I don't have a better answer to give at this point.
Thank you, sir. Any other question, Professor Rao?
Pardon me?
Any questions?
No, I just want to ask him, where is Siddharth now?
Sorry?
Where is Siddharth?
Siddharth is in TIFR right now. He'll be finishing up in about 6 months. This is a former student of Chennai Mathematical Institute, whose name you might have heard, Siddharth Bhandari. Siddharth and Shannon recently, about a year ago, wrote a paper which was a big breakthrough in the area of random sampling. He learned many things, including perhaps information theory from Professor Rao at CMI. And yeah, so sometimes he praises me by saying your lecture was almost as good as Professor Rao.
Oh, thank you.
Yeah.
Your lecture was excellent.
Sorry, so please go ahead. It's okay if you ask strange questions. I'll be happy to.
So there's one more question in the chat. So what if you choose to project to R power D? What if you choose to project R power D to R power D minus 1? Is N power D minus 1 less than P1, P2, P power D, where things are appropriately defined?
Yes, you get, not just R power D. Yeah, so you take points in R power D, then you take a projection of the first 7 coordinates. So R to the power 7. Yeah. In another projection, you take R to the D minus 1. That is everything except the last coordinate. In something else, everything except the middle 5 coordinates. You do this. And suppose it is the case that every coordinate, let's say, so your R power D, the coordinates were x1, x2, x3, xd. If x1 is available from 20 sources, x2 is also available from 20 sources. Each bit of information in X is available from 20 sources. Close your eyes and write the inequality that the product of these projection sizes is at least n to the power 20. Now, in the case of R to the power D minus 1, each piece of information that goes into a point is described by D pieces of information. Each piece is available from D minus 1 sources. So n to the power D minus 1 is less than or equal to the product. You don't have to do anything. And it is exactly the same proof, same conditioning. It is all, once you do the hard work, of using arithmetic mean, geometric mean once in your life. After that, you can just happily enjoy the beauty of entropy and conditional. And make up your own problems, come up with your own inequalities. I suppose all these are called Loomis-Whitney inequalities. So unfortunately, that part is taken, but you might be able to make other discoveries using similar ideas.
Thank you, sir. That was a great answer. So if you still do have, I'm sure. Oh, I see one more question. Could you explain the limit you derived from the Cartesian product? Ayan Ghosh, I'm not sure which one you're talking about. Could you unmute?
Okay, so let me do this. Yeah. So let me stop sharing. Yeah. And go to my board. Yeah. This somehow always behaves. Yeah. It is kinder to me. And can you, is it possible for me to somehow, so am I visible? Yeah. Can you hear me? Yeah.
Yes, sir, we can hear you. Can you hear us?
Yeah, so we can hear you. Everything is fine.
Okay.
I wish I had done this right from the beginning. So this is a to the power n, all possibilities. And how many possibilities are there? A to the power n. Now, if I change n, if I take a bigger n, I will get more possibilities. Yeah? And even bigger n, even more possibilities. Now here, each of the strings has a certain probability. And I've asked you to collect enough strings so that your total probability is 0.9. Yeah. And now this was a to the power n prime. And I wanted you to collect enough probability so that the total probability is at least 0.9 in this experiment. Okay, it's related to this experiment, but just a little longer. And you get a certain number. So here you got, so the number of elements you had to pick was Ln. This was L of n prime, and so on. Now, after doing all this computation, let us tabulate or let us draw a graph of how many strings you picked up. When k was 1, sorry, when n was 1, you probably needed to pick all k strings, yeah, because only then you got 90% of the problem. Then you chose this n, you needed a certain number of possibilities, and this possibility was L of n. And in this, it was L of n. And it will turn out that as you make n large, this will start looking like an exponential curve. The question is, it is exponential with what base? It is not k to the power n. K to the power n is growing like this. The base of this exponent is the entropy of x. In other words, if you take Ln and you take its log, you will get n times the entropy. So if you divide this by n and take large n, and that's why you say limit as n tends to infinity, this will become entropy. That's all I wanted to say.
Oh, thank you, sir. This was a really good explanation. Thank you very much for that. So I'm sure like there will be quite a few questions based on the amount of information you have got in this section. So please do feel free to write to us, and we will get it answered by Professor Jaikumar. And also, Vidyan, any questions?
Log is also log base 2.
So the entropy in information theory is usually defined log to the base 2. But if you just change to a different base, it's just a constant factor. So you don't, worry too much.
In that formula, that hx where limit tends to infinite, that log, that is base 2. So a constant term would change the formula.
Log is
Okay, sir. Thank you. Okay, sir. Thank you.
So yeah, so I hope you got some information from the talk. And so should we say goodbye? Should we wait?
Yeah, I think this was a really informative session, like I said, and also it made us realize how much we miss blackboards over the past year at least.
Yeah, no,
Thank you for that.
At some point I debated using the blackboard, and somehow so I thought I was capable of handling technology and not. Yeah, next time I'll use the blackboard.
Thank you, sir. This absolutely was a really great lecture. So thank you very much once again. So we now meet at 2:30 p.m. next when Professor Manjunath Krishnapur of the Indian Institute of Science will be delivering a lecture titled Statistics for Everyone, where he attempts to give you a non-direct introduction to what statistics is, a new approach to statistics. So we hope to see all of you there, and thank you very much for joining. And thank you, special thanks to Professor Jaikumar.
Thank you.
Thank you, sir.
Bye.